Hello and welcome to the last part of our discussion on statistical inference and hypothesis testing. We're slowly building up towards a more, realistic use of hypothesis testing, as we'll see with the upcoming videos. But the groundwork was laid in the previous two parts to this little subtopic. So we're going to wrap it up with this one by improving on our previous hypothesis testing strategy. How can we improve it? Well, previously we had a distribution of the population of individuals over here, and in our previous examples, we would sample one individual and then investigate that individual, their sample score, and make a conclusion based on that evidence. However, we're not restricted to just looking at a single sample score. We can take a larger sample from this population and measure that by way of its sample mean. So if I take a sample and I do it in an appropriate way, and there are ways to make sure that it's representative to the best of my ability, I will skip over that. All our samples are hopefully a good representation of the population as a whole. So you see here, let's suppose the population follows whatever I'm measuring, some normal distribution. And then you see here the sample is sort of trying to follow that. It's a representative sample. And by looking instead not at an individual score for our sample, but a larger sample, and the sample mean, let's write here, sample mean, and investigate that as the evidence, we have a more representative, what shall we say? Well, sample, more representative information. And we can be more confident in our conclusion versus just taking an individual and hoping that individual has all the characteristics that the population has. But of course, if you think about people, there could be a wide variety of people and different properties across this population, and in your sample you want everyone to be represented so that your sample mean, or whatever you're measuring, captures the population as accurately as possible. However, there's a slight adjustment that we have to make. That previously, if my sample consists of just one individual, then the comparison distribution is the same, the distribution of the population individual. But if I'm going to look at evidence in terms of my sample mean, then I have to compare that to the distribution of all possible means I could get of that size, called the distribution of means. And that is now going to become my comparison distribution. So that's one adjustment we have to make. That if I look at a sample, I'm comparing that against all samples that I could get. And look at how those samples are distributed, not the individuals. Now, luckily, these two have the same mean mu, but as the picture tries to illustrate here, their variance, how quickly it drops off, is not the same. So we just need to be aware of that the distribution of means, my comparison distribution, pretty much from now on, has a different variance. But luckily, it is very closely related to the population's variance. So we're going to distinguish between these two. The distribution of means will have a little m here, and my population distribution will not. So I have this very simple relationship between the variance of the distribution of means and the population variance. The distribution of means has a variance equal to the variance of the population of individuals divided by the sample size. Sample size. And this also shows one thing that is important to note. For a larger sample, what would happen to the variance of this new distribution of means? Well, if the population variance is the same, and I take larger and larger samples, I'll say sigma m squared, my distribution of means variance will get smaller, which means, well, does it make sense? Because I'm taking a larger and larger sample, sort of drifting towards, but never getting there, drifting towards the whole population. The variation between samples are going to be less and less. It's going to be more smoothed out because I include more individuals. And this relationship fits that observation, rather. So over here, I just have some examples. If my sample size is 2, I have a population variance of 12, for example, randomly. If my sample size is 2, I just make the adjustment by dividing by 2. I get the variance of the distribution of means. And you see here, the larger the sample size, the lower that variance is visually or graphically, the tighter this distribution is. I am much less likely to get sample means far away from the mean if I take larger samples. Okay, so we'll refer back to this in a little while. So let's just have a look and think about this again, just to sum it up. I start with my distribution of the population of individuals. I'm trying to say something about all people in the country in terms of some property or whatever. However, I'm going to do that by taking a sample of hopefully large, but not necessarily super large, big. It depends on what I can do practically, what my budget is, all kinds of stuff. I have a sample of more than one. When I investigate that sample, I have to essentially measure it against the distribution of means of that sample, of that size sample, rather. These distributions will have the same mean, the population of individuals, and the distribution of means. The variance will be a little less, depending on the sample size we just saw. So I have to remember that, right? My variance for this comparison distribution is the variance of the distribution of population of individuals over the sample size. The interesting thing, and this is a fundamental theorem in statistics, is that regardless of the distribution of the population of individuals, which could be normal, but not necessarily. If my sample is large enough, 30 or more, then the distribution of means is approximately normal. So there's a humongous benefit opening this up to have a much larger scope, that I might be measuring something that is not normally distributed among people. But for a large enough sample, the distribution of means, my comparison distribution, is a normal distribution, which means it could come from a variety of places, but I'm mainly looking at this bell curve, which is super convenient. Let's emphasize that a little bit with the following little table, just to see the different possibilities. So I have a population. It has just random numbers for the mean, really completely irrelevant. The number could be anything. I have a standard deviation here for the distribution of the population. Of course, the variance will just be that squared, so I'll just have a 400. My pen can be a little smaller, huh? It's a little thick. Maybe that's a little better. Yeah. And these are all 20, so this will all be 400. So let me just fill this in. 16 squared is 256, 11 squared 121, and so on. I should have filled that in already, to be fair. Okay, so let's look at this one. If the shape or the distribution of the population of individuals is not normal, some other distribution, but my sample size is big enough, then the distribution of means will be normal. Its parameters, the mean is the same. The variance will be the population variance over the sample size, which is 4. And then the standard deviation is just the square root of that, right? Square root of that. So hopefully I can fit all this in. We'll see. So the next one, if my population distribution is normal already, then it doesn't matter what the sample size is. The distribution of means will also be normal. I'll fill in this one too, I suppose. Same mean. The variance of the distribution of means will be the variance divided by the sample size. And I'll let you finish that. Doesn't matter. Don't want to waste your time. Straightforward, I hope. If the next one, if the population of individuals is not normally distributed, I have to look at my sample size. If my sample size is, what did we say, 30 or more, then our distribution of means will be approximately normal. This one, however, is only 10. So let's make a better no there. I will not have a normal shape. I'll have something else, and I would have to see what that is and go another way. However, the parameters are still the same. I still have the same mean. I still have the variance being the population variance divided by the sample size, and so on. It's just I don't know if it's a normal distribution. In fact, if it's not, it's not. And it's not close enough to use it as an approximation. If the population distribution was normal, the sample size doesn't matter. The distribution of means will be as well. Same parameters. I'll leave that to you. I'll emphasize here 24. And the new variance is 256 divided by the sample size of 8. Blah, blah, blah. And lastly, if the population is not normally distributed, but I have a large enough sample, 30 or more, and I do, then the distribution of means is very close to normal. And that's sort of the agreed upon cutoff, 30. And I can go ahead with my z-scores and all those familiar things. 121 divided by 48. And you can calculate those things. So 30 is my cutoff. If I have a large enough sample, I do not have to worry. It's normal, the comparison distribution. So that is very convenient. Okay, so keep that in mind. Now, right now, we only know how to handle a comparison distribution that is normal. So if it's not, then more advanced things are needed that we can't address all at once, of course. So just to sum it up, here we have the population distribution. Our sample itself has statistics, mean, variance, standard deviation, and I'll use that, but on the distribution of means, which has parameters same as the population, mean, variance slightly adjusted by sample size. Then, of course, I can get the standard deviation, and that distribution is normal if I have at least 30 as my sample size. All right. So let's look at an example. It's a little wordy, but bear with me. I just took this from one of our books. So let's see, we're trying to investigate whether being told that a person has positive personality qualities increases their physical attractiveness by some score. So we have a sample of 64 people that we're investigating this property, and they are rating attractiveness based on a person's photograph. Prior to rating this attractiveness, each of them are told that the person has positive personality qualities, and we're trying to see, does that affect the attractiveness score that they give? On a scale of 0 to 400, the mean attractiveness rating given by the sample was 220, so that's my sample mean. And from prior research, that we can take as fact that the distribution of attractiveness ratings of people in photographs with no mention, just the population, those ratings have a mean of 200, so that's my population distribution mean, and a standard deviation of 48. And they follow an approximately normal distribution. But in fact, because our sample is large enough, that information doesn't really matter. I guess when we want to draw it, it does. So we want to remember these numbers. The population of individuals distribution, 200, mean 48, sigma, standard deviation, and our sample mean is 220. Pause here if you need to read it again, of course. So now we're going to set this up, and we're trying to compare students who are being told that the person has a positive personality, or positive personality qualities rather, against people that are told nothing. And our research hypothesis, what we kind of want to be true, or we hope that this information increases the average attractiveness rating, against the null hypothesis that it does not. So our setup is very similar. It's just our comparison distribution is now the distribution of means. So I have a sample of 64. Let's see if I can zoom in on that. I think we can do a little zoom for sure. I have a sample size of 64, sample mean of 220, and my population of individuals that I'm sort of measuring this against, it has a mean of 200, standard deviation of 48. Shape unknown. Didn't they say it's approximately normal? Yeah, so let's just fix that. I don't actually care in this case. It's approximately normal, they say. Because our sample size is large enough, I actually don't care. So for the comparison distribution, the distributions of all means of size 64, the distribution of all means of samples of size 64 have the same mean as the population of individuals. Different variance, taking the population variance dividing by the sample size, which we do there, and we get 36. Standard deviation, of course, we need standard deviation for our z-scores. Square root gives us a 6. The shape of this comparison distribution is normal because my sample size is large enough. That's not really necessary because I had a normal distribution for my population anyway. So we win either way. Sample's large enough and we have normal. So definitely our comparison distribution is normal. So now remember what this what I can visualize this as, right? Let's maybe visualize it first. What are we actually doing? Well, we have our, zoom in on this. Zoom. We have our population distribution here, but that's not actually the distribution we're looking at. We're looking at the distribution of means. We're going to have, I think, 5% here for our alpha as our confidence level. That gives us our familiar z cutoff. I'm just trying to see where I can write this. Maybe over there. Z cutoff that we looked it up in the tables last time. What was it? 1.64. And then we're going to look at our sample and ask, where does this sample that we have fall in the distribution of all the samples that are possible? If this distribution is true and the population, knowing the positive personality information doesn't actually change anything to the attractiveness rating, we would expect samples over here somewhere, right? Yeah, it's not going to be exactly at the center. Of course, there's some variation, but we don't expect a lot. In fact, within this cutoff, we're going to expect 95% of all the samples we could possibly get will fall in here. We now look at our sample. Our sample gives an average, a sample mean score of 220. Where does that sit? Well, let's just do a calculation and then visualize this again. So we have our cutoff. We decide on a 5% confidence level. We do our sample. We calculate our sample score. The mean is going to be, take the mean, sample mean minus distribution mean over 6, which is our standard deviation for this distribution. We get 3.33. 3. That puts us way out there. Now we can argue that if this sample is representative, this is very rare to get. Perhaps it's a fluke, or perhaps the distribution of the population, the distribution of people that have this extra personality information isn't actually over here. It's not centered at the same mean, but maybe it's shifted a little bit over. For me to get a sample like this, it's going to sit somewhere over here. That is a terrible drawing of a normal curve. It's maybe going to sit somewhere over here, right? I expect samples to be close to the mean. For me to get a sample way out there under the assumption that this is the distribution is so rare, it provides evidence that suggests that this is not what's happening. This is not, the means are not the same. So we could say a variety of things. This is much more extreme than the cutoff. Therefore, we reject the null hypothesis in favor of the research hypothesis. It doesn't prove the research hypothesis. I emphasize that every time. The evidence supports the research hypothesis that, in fact, the mean of people that are given this positive personality information is bigger than my comparison distribution mean. And the mean for that group of people, yes, in terms of the mean, but still is a little further to the right. To justify that I would just get a sample like this in a rare situation, it's too unlikely to bet on. But it will probably come from a distribution that sits further to the right with a mean that is greater than the second population mean. All right, so our general hypothesis testing thought process is the same, except we have better information by looking at a sample than if we just took an individual. The variation in that individual score is much bigger. And if we have a lot of variation, then we could just have bad luck and get a sample that is that rare. But by switching to a sample, we're looking at a distribution that has a much smaller variance, much less variation. For us to then get something extreme, it provides much stronger evidence. All right. That is the idea. Okay, I think the next page is just blank. Okay. So another question we could ask is to provide an approximation. Let's say, oh, now my pen is not thick enough. Maybe this. Yeah. Get an approximation for I should try and write neater. It's a challenge. For the true mean of this population, I have established that, look, it is more than telling people nothing. The mean attractiveness rating increases, or the evidence suggests that it increases with this extra information. But now what is it? Well, we can use our sample, oops, the wrong page. We can use our sample mean to provide an estimate, an interval that contains the mean, we'll call it mu1, somewhere in here. Somewhere in here. We don't know exactly where. The best we can really do is to build this around our sample mean, m. Now, what was m? M was, I believe, 220. Let's double check. Yeah, it's over here. M was 220. Assuming that our sample is representative of the actual population, population 1, it suggests that population 1 is different from population 2. Having this extra information definitely, well, not definitely, seems to change things. Change it to what? Right? If it's different than the 200 mean from population 2, well, what is it? We're going to have to try and get a range of values that approximate it. However, if we look at the distribution, let's make a new graph over here. I'll attempt to draw a normal curve for population 1. The symmetry is the challenge. There we go. All we can do is say, well, let's build it around our sample mean. We might luck out, and the true population mean is exactly 220, but we don't know that. We hope our sample is representative, and then it should be close to this, but we can't say for sure how close. Well, if it's a normal distribution, we can say, let's at least be 95%. Let's catch 95% of the possible means around this estimate. So then, of course, this is 2.5%, 2.5%, and we saw last time that corresponded to a z-score of 1.96. And of course, then this is negative 1.96. So yes, I'm mixing the scores with z-scores, but that's okay. Let's say here z over there. Okay. So let's at least catch as many as is reasonable. Well, then we can build these intervals by taking the mean. Let's say it symbolically first, and just calculating the corresponding score for this, which will be the z-score, well, it doesn't matter, times the distribution of this, the standard deviation of this distribution, right? So we build it slowly out from our best guess. If we do that, of course, this is 220 plus our 1.96. You maybe swap the sigma and the z-score, doesn't matter, times, what was sigma m? I don't remember. I think it was 6. And we should get 231.76. And I'll put that in here, 231.76. And if we do the other one, and I'll show it in a second, we'll get 208.24. So this interval we'll call it the 95% confidence interval for obvious reasons. That based on our sample mean, we have a 95% chance of catching the true population mean. Remember, the distribution of means and the population distribution have the same mean. So it's totally fine to look at the distribution of means instead, and that's the one we have information of. So I'll say again, using our best guess of the using our best guess of the mean, the sample mean of 220, we build an interval around that to have a 95% chance of containing the true population mean, because it contains 95% of all possible sample means. Now, of course, we could change the alpha to something else, but this is the idea. By way of a confidence interval, we establish a range, an interval that hopefully captures the true population mean. So let's actually do it this way. And I have two of them here for 95% confidence and 99. We're building an interval around our estimated mean, understanding that our sample mean might not be the exact true population mean. Of course, there's going to be some variability, right? So we build, let's say, a 95% confidence interval in the way that I just said. Lower limit, we'll use the left z-score times the standard deviation plus our center mean, and we get these two values over here. You could have also done a 99% confidence interval, and then that goes a little bit further, and the further out you go, the more confident you'll be that you have the true population mean in your interval. But of course, the downside is it gets bigger, so it loses some meaning. If you just make your interval infinitely big, of course you're going to get it, but it's not really useful. Okay, confidence interval. So here I'm just picturing this again and giving some steps if you want. I have to, of course, be aware of my appropriate standard deviation. And if I have to choose my confidence level, just like I choose the alpha in the hypothesis test. These are very closely linked. And then I find the corresponding z-score for that confidence level and calculate the corresponding scores or raw scores, and that establishes my confidence interval. All right. Now, in the case of a two-tailed test, I know that wasn't quite our example, but let's pretend we didn't know if the average attractiveness rating would increase or decrease given positive personality information. We could also use the confidence interval to get to the same conclusion as the hypothesis test conclusion. They'll always agree. In the case of the two-tailed test, of course. So if we pick an alpha of 95%, of 5% rather, and establish this confidence interval, I'll just write over here, this one corresponds to a raw score of 208.24, this one 231.76, and then I can look at my null hypothesis, not necessarily the null hypothesis rather, but the population, the original population, the population with no extra information. I think we numbered that population 2. was 200, wasn't it? I think. Whoop, the 200. Yes, over here, 200. We can then use the confidence interval. I'll scratch that out. It's something for later. We can use our confidence interval and say, well, we're 95% confident that based on all our evidence, the population mean mu1 falls somewhere in this interval. If we look at the mean of 200, that does not fall in this interval. The mean of 200 sits outside of that. That suggests that they are significantly different. In fact, the mu1, the population 1 mean, is, well, the evidence suggests that it is greater than the 200 of population 2. So let's say here, since mu2 falls outside my confidence, I want to write a C there, confidence interval, we can conclude the same, or we can make the same conclusion as the hypothesis test does. And that's always going to happen. I can use the interval, the confidence interval, of course using the same alpha, right? Confidence interval with the same confidence level, that if I establish the confidence interval and the mean of the, let's say the base population, falls outside of that, that means that this property that the new population has, being told that the person has positive personality traits, that pushed the mean to shift outside, far enough away from the 200 in this case, that it is considered significant that a change did occur. If the mu2, if the base population mean still fell inside this interval, that would correspond to inconclusive evidence. And our hypothesis test would have a, is that the picture? Would have a sample score that falls with not outside the cutoff, but within. And those two will always get us to the same conclusion. Of course, if it's a two-tailed test, because the confidence interval is always two-tailed. I always do both sides to get an interval. So we'll do this more as we go. Doing the hypothesis test procedure is definitely the more important one. But every now and then we'll look at how the confidence interval, or what the confidence interval is, and use that as an alternative interpretation, leading us to the same conclusion as the hypothesis test. All right. So think about this. Let me know if you have any questions. And we will slowly move on through this statistics course. Until later.